Section 6.2, example 9, differentiating power series. So use the power series representation of f of x for x, or absolute value of x being less than 1, to find the power series representation for g of x on the interval from -1 to 1. Determine whether the resulting series converges at its endpoints. All right, this is part B. Let's shift this down just to give us a little bit more room to work with. We'll shift it right back up. I promise. All right, so use the power series of the representation. So main thing, differentiating. And what I do notice is that when we differentiate f of x, we get g of x. So let's do that computation really quick. So f of x equaling 1 over 1 minus x, right? 1 over 1 minus x. F prime of x, we could see this as like 1 minus x to the -1. Power rule, we grab that exponent, bring it to the down as a coefficient, and then we multiply this, subtract 1 from the exponent, and then we take the derivative of the inside, which is -1. So looking at this, we end up with 1 minus x squared in the denominator. Numerator, the negatives multiply out, so we have a positive f prime of x, which is actually equal to g of x. So now that we have that, let's take a look at the power series, s of x. So looking at s of x, we have the sum as n goes from 0 to infinity. Our first term is 1, so we don't have to write that down. X to the power n. So now what I want to do is take the derivative of both sides. So derivative with respect to x. Same thing here. We're taking the derivative with respect to x. So the way that I'm going to state this one is s prime, oh, actually, no, yeah. S prime of x is equal to, here we still have the sum as n goes from 0 to infinity. Now we can multiply this down, so we have n times x to the n minus 1. X to the n minus 1. So we could leave this like this. I don't really like that we have that -1 there. So what we're going to do is shift this over. So when we plug 0 in here, this ends up being 0. Or we could shift this to start at, actually, no, we could still let it start at 0. And starts at 0 up to infinity. Let's shift this to an n plus 1. So that way we could leave this as an n. So that way when we plug 0 in, 1 is our first term. And yep, there we go. So now what we could do from here is state that g of x, since it's the derivative of f of x, this sum is the derivative that came originally from f of x. We could state g of x as being this right here. The sum going as n goes from 1, I'm sorry, as n goes from 0 to infinity of n plus 1 times x to the power n. All right, I like that. So power series for this power series here. All right, so now that we have that, let's take a look at part B. So use the result from part A to evaluate the sum of the series here. All right, so I'm not too crazy about that notation. What I really want to do is find an equivalent function or equivalent sum. Sum as n goes from 0 to infinity. N plus 1 over 4 to the power n. Because we have that n plus 1, and because I know that this here is that sequence, I feel like we could use this to turn it back into a function here. But we have to kind of put it in this notation. So we need an x that we could raise to the power n. All right, so looking at that, we could state this as the sum as n goes from 0 to infinity. Let's pull out that n plus 1. And we could rewrite this as 1 over 4 to the power n. And now that we have that, we could actually use that right over here and say that the sum as n goes from 0 to infinity, n plus 1, 1 over 4 to the power n. We could equate this to 1 over 1 minus x, and in this case, x is at 1 over 4 squared. Oh, we could actually find a full value here. So that's 1 over 3 over 4 squared, which is equal to 16, or we could, 16 over 9. Just multiplying by the reciprocal. Let me lower this a little bit. And there we go. That's our infinite sum there. So we actually got a value for the first time, I think, in this whole chapter. And there we go. If you have any questions, please do not hesitate to ask. Otherwise, bye.